So hello everyone, this is Saja Al-Dabet from United Arab Emirates University. Today I will present our paper titled as Dual Task Learning for AI-Generated Medical Text Detection and Named Entity Recognition. This work was done by me, Saja, with my colleague Ban, and also Dr. Sherzod, Turaev, and Dr. Abdelkader Belkacem. So the agenda for this presentation will be as follows. We will start by introducing the topic, the proposed methodology, experimental results discussion, and also to conclude this work. So as you have seen since the morning, we are talking about large language models, how they are transforming the tasks, how we can use them. For sure, one of the benefits of large language models has been happened in the medical field, where we can have key applications like automated report generation, clinical documentation, and also dissemination of medical information. But at the same time, as our previous presenter has already noted, that we have some key concerns regarding the accuracy, the reliability, and also the authenticity, especially when we are talking about the medical field. So there is a huge risk to have a kind of misleading AI content at the same time for patient care, and also if we are using them also for the medical field, there is also a kind of misleading information in this case. So to deal with this issue, actually, the researchers have already put an effort in this, in distinguishing actually or differentiation between the human written text and also the AI generated text. The previous research has been already noted that there is a kind of key main differences between the AI generated text and also the human generated text in terms of vocabulary, sentiment, AI generated, and also the linguistic part, where, for example, in terms of vocabulary, the human written text is more diverse and has more detailed vocabulary, while the AI generated one could be used, for example, most common, for example, words based on the training part on those models. Also the sentiment, where the AI text tends to be more neutral or positive, while it's not even the case always. Also in terms of linguistics, AI generated text could have more nouns, more plural nouns, more conjunctions than the written by a human, and also the way of describing, for example, the text itself, a human may tend to use adverbs and more specificity inside the text itself. So in general, there is a lot of work in this area for the differentiation between AI generated text and the human text, and also for a task called medical named entity recognition. I will not go through all of them because of the time limitation, but in general, those research papers have been actually developed using, for example, different types of large language models or deep learning, machine learning large language models. Actually, we have found that there is still a gap and limitation in the existing approaches in the medical field specifically. That's actually encouraged and motivated us to propose a solution or an architecture using ELECTRA model that was developed by Clark in 2020 to address this challenge. And we have proposed a model or an architecture, more precisely, that do two tasks at the same time, which is, first of all, do the text classification or text differentiation between the human written and the AI generated text, and also it takes the advantage of medical named entity recognition to recognize those entities, and it take a shared knowledge between the named entity recognition task and also at the same time for the differentiation tasks. Actually, for evaluation purpose, we have tested this model using a radiology reports dataset and medical dataset for that purpose. So let's move to the important stuff, which is the proposed architecture in general. Here you can see the general architecture, where we are starting by pre-processing the data and also have a kind of shared training for the ELECTRA model. We call it a backbone for our model. And then we have divided the model to be one, we have extracted actually the attention heads for named entity recognition and also for the classification task, and also evaluated each one alone. So let's see what was happened during the data pre-processing. We have started for sure by cleaning the data, identification of any null entries, tokenization, removing any special characters. But the most important part was the medical named entity recognition annotation, where we have used the model from Spacey library, pre-trained model. That model actually helps us to annotate our data with 7 entities. You can see an example here. So for example, we can annotate our data using this model. So we have 7 entities, which are root, drug, and frequency, duration. At the same time, you can annotate the data and extract another file from that data. So we went through this annotation process. And after that, for sure, we have encoded our data and our label. So that happened here in the blue area. After that, we moved the output from that pre-processing to the model itself, where we have applied ELECTRA model. Why ELECTRA model? Actually, not any model, a large language model. Actually, ELECTRA, it's a kind of models that is similar to BERT, for example. It's a pre-training approach with encoder-decoder, but the key difference here is that instead of masking random tokens, ELECTRA model actually replaces specific tokens with the plausible alternatives, which are generated by the generator part. This is for generator. The discriminator is the regular discriminator, which identifies actually each token. Is it the original token or it's the replaced token? This approach or this model in general have been shown and promising results in different tasks in terms of efficiency and effectiveness of performance. We have trained this model for the both tasks to take the advantage of the hidden states for both tasks, the named entity recognition. So we have those entities, the medical entities. So we take the benefit from those NER tags and reflecting them to the original text to see how that will help us to differentiate between the AI text generated and also the human text. After that, we have extracted the heads for named entity recognition and produced the output. And at the same time, we did the same thing for differentiation or the classification of AI generated text and also the human text. So to evaluate this approach or this architecture, we have utilized a data set that has 2 subsets in general. It's a medical data set. The first part of the data set or the first subset, actually, it's a medical abstract from medical papers. It's available on Kaggle. And also we have used the second one, which is a radiology report. This data set contains actually selected radiology reports. In general, both data sets together comprising around 4,400 instances. Those instances have been took and the author here, Leo, sorry, has generated an equivalent also amount generated by ChatGPT. So at the end of the day, we have a full data set that is labeled with the human text and AI generated text. We have actually divided the data set to be for training, testing, and validation purpose. For the experimental settings in general, we have trained our ELECTRA model to do the dual task, both tasks, which is a combination of named entity recognition and also the identification. For the classification, we have 2 main primary labels, which are the human and the AI generated text. And for the NER task, we have those seven labels. So let's move on to the experimental results. You can see the table here. For the first part, we are previewing the classification task or the differentiation task between the human text and AI generated text. And in the second part, it's the medical named entity recognition. As you can see, we have evaluated and compared our work with the state-of-the-art works with the artwork, where some of them have used, for example, BERT, Albert, and BioBERT, Robert, or something else in terms of large language models. And we have tested also for sure the ELECTRA model. As you can see in terms of accuracy and F1 measure, for the first data set, which is the medical data set, the medical abstracts, I mean, we have a competitive and general output. in general, we have competitive performance in general, and also for the mimic, which is the radiology data set, we have also a stable in general and a comparable performance in comparison to other models in the literature. And also we have tried these settings with BioBERT, Robert, and XLNet network. For the named entity recognition, it was more challenging, specifically for the classification task. For all models, we have tried multiple models, but it seems that the medical abstracts were more challenging than the mimic or the radiology reports in general, where in radiology reports, we got a stable performance. However, there is a room for sure for enhancement here for the medical abstracts from medical papers. As you can see here also the ROC values for the classification, it was stable for even in the named entity recognition for
Sorry, we have to wrap it up.
Yeah, I'm sure. I'm sorry. And here you can see the ROC values. Here you can see we have utilized the Lime explainable model. We took the learned weight and tested them. For example, here in the first example, the abstract tends to be more generated by GPT than the human, while in the second case, it tends to be by human more than the GPT. Here we have also done a kind of evaluation for name entity recognition task alone, and as you can see, the ELECTRA model is still capable to recognize those named entity recognition, and there is still a room for improvement for sure. To conclude, we have proposed a dual task learning model using ELECTRA model. The integration actually helped us to get better performance in classification, but there is still a room for named entity recognition task. In the future work, we can try more complex scenarios with medical stuff. Thanks for listening, and a question, please.